Have you ever heard that some bacteria in soils breathe iron? Although this sounds kind of strange, it happens. But where? It happens in soils that are lacking oxygen. For example, soils that are periodically water saturated or flooded. Let's look at one of them. When it is flooded, there is no oxygen in it. Then, some bacteria use iron in a kind of respiratory process, like we humans do when breathing oxygen.
Almost all soils on Earth contain iron, usually about 1 to 5 weight%. And if soils are in contact with air, iron gets oxidized and it forms iron oxide minerals. These are usually yellowish brown to orange in color, and we can easily see them in the soil profile by this color. It's very similar to rust.
When a soil is flooded, the oxygen is used up quickly. Then bacteria in the soil start to reduce this iron.
And then these oxide minerals dissolve or are transformed to other minerals, like for example iron carbonates, iron phosphates, or iron sulfides. Now all of these iron minerals in soils consist of very tiny particles, usually about 10,000 times smaller than a sand grain. And therefore they have very large surface areas which can bind other elements, including environmental contaminants like heavy metals, nutrients like phosphate, and also carbon. In our project, we are interested in understanding better how these iron mineral transformation processes happen in natural environments, especially in soils that are regularly flooded and drained. And we developed new methods to be able to follow these processes directly in the field, which has been previously only been possible in the laboratory.
Soil is a good information source about environmental processes. But what stories can the iron in periodically flooded soils tell us? In laboratory studies, it was discovered that under certain conditions, iron minerals can change their properties very quickly. Now, the soil scientists at ETH Zurich investigate how these iron mineral dynamics are happening in the field. The ERC-funded Nominee project helps to answer important practical questions. Let's look at 3 examples. First, many periodically flooded soils are contaminated, like floodplain soils or rice paddies that feed many people worldwide. Nominee helps to answer the question, how do the contaminants in these soils behave? And how do they interact with iron minerals? Second, soils regulate nutrient availability in ecosystems. Nominee helps to answer the question, how do iron mineral transformation processes influence the behavior of nutrients in soils? Third, stabilization in carbon is one important aspect in reducing global warming. Nominee helps to answer the question, how could iron minerals work as a carbon sink in periodically flooded soils like salt marshes? The Nominee project explores 3 different field sites: rice paddy soils in China and Thailand, organic and iron-rich wetlands in Iceland, and salt marshes in the German Wadden Sea. But how can they squeeze useful information out of the mud? How can they study the behavior of iron minerals in the natural soil? They have to introduce iron mineral samples into the soil in a special way so that they can react undisturbed during several ebb and flood cycles. and the samples need to contain traceable components. In fact, they need material which doesn't exist naturally in the soil, but behaves naturally. Firstly, this material has to be produced in the lab.
We synthesize different iron minerals, which also occur in nature. But unlike in nature, we make them from almost pure iron-57. Iron-57 is a specific isotope of iron, and it behaves just like the iron, which is naturally present in the soil. So we can use this isotope to trace the changes in our minerals. Here, for example, I'm making ferrihydrite. Ferrihydrite is a mineral which is present in almost all soils. It has a very large surface area, and it can effectively bind pollutants and nutrients. And this is why it is so important to explore the behavior of ferrihydrite.
Secondly, the synthesized and dried iron mineral is mixed with natural soil. And this mixture is put into a mesh bag, so the iron mineral has maximum contact to the surrounding soil when the sample is placed in the field.
This imitates the fine distribution of the iron mineral in the soil, so microbes and the pore water can react naturally with our sample. Some iron minerals are sensitive to oxidation. In this case, we have to do this work in an oxygen-free glove box.
The next step is crucial for investigating soil processes in the field. How should the soil mixture in the mesh bag be introduced without disturbing the natural soil layering? To solve this problem, the Ermidine team developed special sample holders. They minimize the disturbance caused by the samples.
Because of their shape, we call them rockets. They have a point that allows us to insert them easily into soil, and because they're connected to a rod, we could find them easily after several weeks in the field.
After the rockets are hardened under UV light, they are filled with the mesh bags. Now they are ready for the field experiment. Fieldwork is teamwork. A lot of equipment has to be carried to the field sites. Besides the rocket installation, the team is taking soil cores for characterizing the study area. Another important task during the fieldwork is to collect and analyze pore water.
Maybe like 50 ppm, something like that.
Now it is time for the rockets to enter the soil.
Here we are installing our field experiments. So this is made of the mesh bag, which contains our mineral, or the 57 labeled mineral, inside this rocket cage. And we insert this into the sediment at a depth of 15 centimeters. And so here in a few hours, the tide will rise, and then this will mean that the oxygen, which is currently stored in the sediment, will be used up. And then in another few hours, the tide will ebb, and more oxygen will enter the sediments, and so on. And we're interested in what these processes will mean for the minerals that we've buried here.
After several weeks, the team members return to the field site. They have to collect the samples again. To prevent them from reacting with atmospheric oxygen, they are vacuum sealed immediately. The final step takes place in the laboratory. Have the iron 57 labelled minerals changed? And if yes, how?
Now we finally have our samples back in the lab, and we want to know what happened to our 57 iron minerals. With Mossbauer spectroscopy, we can selectively detect 57 iron. It gives us information on its oxidation state and mineral identity. This allows us to investigate how the mineral was transformed during several weeks in the soil.
For the Mossbauer spectroscopy, some samples have to be cooled down to a range between 5 and 20 Kelvin. This is below minus 250 degrees Celsius. And indeed, the minerals have transformed to other iron minerals within only several weeks. This is an exciting finding for the scientists. But they have to confirm these results by other methods, such as X-ray diffraction and Raman spectroscopy. At the end, the ETH scientists not only gained new information about the effect of iron minerals on contaminants, nutrients, and carbon, they also developed a novel approach to study iron mineral transformations directly in soils and sediments. For the scientists, this new method is like a key that opens up many new doors for research. For example, about the behavior of iron minerals and their roles in the environment. A few doors are already unlocked.
We used this new method to follow the transformations of iron oxide minerals in rice paddy soils. In these soils, iron oxides play an important role as sorbents for phosphate, silicate, and other nutrients.
Some rice paddies become very acidic when drained. With this new method, we are looking at the transformation of jarosite, an important mineral in these environments, and how it may impact the behaviour of contaminants in soil.
In the environment, iron minerals are efficient traps for metal contaminants such as zinc, cadmium, lead, or uranium. And we can now better assess the impact of iron mineral transformations on the mobility and availability of these toxic metals in contaminated soils.
With this approach, we're now investigating how the transformation of an iron mineral is influenced by the minerals that exist in the soil around it.
We are investigating the formation and stability of an iron phosphate mineral in tidal sediments. This helps us to understand phosphorus cycling in the coastal environment and how sea level rise will change it.
Subpolar soils often store huge amounts of organic carbon, and they are therefore very important in the global carbon cycle. Now, volcanic soils, for example in Iceland, additionally have very high iron contents. In our project, we want to understand how iron mineral transformations are influenced by organic carbon and how this in turn affects carbon cycling in these soils.
We are ready for the next adventure. Want to know more about our work?